I want you to just picture this for a second. You're driving down the highway in a hybrid vehicle, right? And you're cruising along in pure electric mode. It's completely silent. And you see this gap in the fast lane, so you press the accelerator to pass. And instantly, like, the internal combustion engine fires up, the power surges, and you just merge.
Yeah, it's perfectly smooth.
Exactly. From the driver's seat, it just feels like this one continuous, seamless motion.
Well, it's an incredible illusion, really. I mean, the illusion of simplicity. Because behind that, that seamless half-second is this brutally violent, like, microsecond-level physical and electrical ballet.
Right, a ballet of, like, explosions and electricity.
Pretty much. You have a gas engine, a primary drive motor, and a generator, and they're all kind of fighting for dominance, but also collaborating at literal lightning speeds.
And so today's deep dive is really looking at what happens when that ballet just catastrophically fails.
Yeah.
We've managed to pull a pretty thick stack of internal engineering failure analyses, DFMEA and PFMEA documents, and they specifically focus on this thing called engine and motor coordination failure in hybrid powertrains.
That's fascinating stuff.
It really is. So we're going to use these blueprints to look at the invisible safety nets that keep these systems from just, well, tearing themselves apart. Because if we look at the raw mechanics of it all, a hybrid powertrain shouldn't really actually work. I mean, it is fundamentally at war with itself from the very moment the engine cranks.
Oh, it really is. So the engine, the drive motor, and the generator, they're physically, mechanically locked together.
Right.
Usually through a planetary gear set. And when the internal combustion engine starts, it doesn't just deliver this smooth, linear application of power.
Because it's literally thousands of tiny explosions.
Exactly. It injects these severe nonlinear torque impulses, the cyclic firing pressures from the cylinders, and it pushes those directly into the drivetrain.
Right. So it constantly disrupting the smooth torque curve that the electric motor is, trying to maintain.
Right.
And the source documents mention that to counter this, the system relies on this thing called active damping.
Yeah, active damping is crucial.
So the controller basically reads the mechanical vibration and instantly applies an anti-phase force from the electric motors to just cancel it out. The analogy that comes to mind is like pushing someone on a swing.
Okay, yeah.
You have to catch the swing at the exact right millisecond to slow it down, right? If you push at the wrong time, it gets chaotic.
That swing analogy gets us halfway there. But in a closed-loop control system like this, the margin for error is just razor thin. I mean, it all comes down to the phase lag in that active damping filter.
The processing delay.
Yes. If the processing delay causes a phase lag of more than 90 degrees, you aren't just, missing the swing. You are pushing it at the exact wrong time. You literally invert the logic. Yeah. So the negative feedback loop, which is supposed to damp the vibration, it actually becomes a positive feedback loop.
Which induces what they call a divergent resonance.
Yeah.
So the vibration just amplifies itself recursively.
Exactly. And within milliseconds, the gear teeth are just aggressively clattering against each other. And if the system doesn't immediately shut down, the transmission shafts will suffer these severe fatigue fractures.
Like the physical metal simply tears itself apart.
It shatters. Yes.
That is wild. And that mechanical stress is just one failure vector. The documents also highlight this massive electrical bottleneck, magnetic saturation.
Right. This is where the physics get incredibly unforgiving. So let's say it's a freezing cold morning, right?
Okay.
And the engine oil is highly viscous. It's like molasses. To force the combustion engine to crank and actually push past that torsional resonance zone we just talked about.
To get through the danger zone quickly.
Exactly. The generator has to pump an enormous amount of electrical current into the stator coils.
So it's pushing maximum amperage, but the analysis states this causes the iron core's magnetic path to saturate.
Yeah.
And that completely breaks the field-oriented control math. Walk me through the mechanism there. Like, how does a solid piece of metal get full of magnetism?
Okay, so down at the atomic level, the iron core is made up of these little magnetic domains. And normally, these domains align with the magnetic field induced by the electrical current.
Okay.
And that's what allows the motor to actually generate torque. But there is a finite physical limit to how many domains can align.
Right.
Once they're all aligned, the metal is officially saturated.
Mm-hmm.
You can pump in as much extra current as you want, but the magnetic flux will not increase.
Oh, I see. So the physical properties of the motor they hit a brick wall.
Well, worse than a brick wall, really. The properties actively degrade.
Wait, really?
Yeah. The inductance, which is basically the motor's resistance to changes in current, it drops non-linearly, sometimes by like 30% to 50%.
Wow. That's a huge drop. And since the controller relies on a mathematical model, right, the field-oriented controller, FOC,
Right, FOC.
since it uses that to predict exactly where the magnetic poles of the spinning rotor are, that model must just instantly decouple from reality.
The math completely breaks down. The control current misaligns with the actual physical magnetic poles.
So it's pushing blind.
Exactly. The torque estimation gets wildly distorted, and the motor just loses its electromagnetic grip on the rotor. The entire system just stalls out in what engineers call a pull-out event.
A pull-out event, okay? Which brings us to the third major failure vector they outline. And this one is tied directly to just the sheer speed of modern EV architecture.
Oh yeah, the screaming silicon chips.
Silicon carbide chips.
Right. Silicon carbide, or SiC switches, they're the absolute backbone of high-efficiency inverters.
Yeah.
They allow power delivery with almost no thermal loss because they transition between on and off states at just blistering speeds.
How fast are we talking?
We're looking at voltage transients exceeding 10,000 volts per microsecond.
10,000 volts flipped in a single microsecond.
Yeah.
That switching frequency is almost incomprehensible. But the documents show there's a severe side effect to all that speed, right? Extreme common mode electromagnetic interference.
Yeah.
It's essentially broadcasting intense electrical static inside the car.
It's like a mini electromagnetic shockwave every single time a switch flips.
Yeah.
And that noise floods the vehicle's low voltage control lines.
Okay.
So it invades the CNFD network, which is the car's internal data bus, and it causes these cyclical redundancy check, or CRC, errors.
So the data packets basically get scrambled.
Yes. So if the main vehicle controller sends a torque command to the inverter just receives corrupted garbage data.
And the notes mention that if this communication frame times out for more than 50 milliseconds, you get these lethal voltage surges. But why does a 50 millisecond drop cause a power surge?
Well, because the delicate balance of power in a hybrid is entirely predicated on real-time consumption. So imagine the generator is pushing, say, 50 kilowatts of power into the high-voltage bus. It's expecting the drive motor to consume that energy instantly.
Right.
But if the drive motor suddenly stops responding to commands because of a 50 millisecond data timeout,
that power has nowhere to go.
Exactly. It instantly cascades into these massive overvoltage surges right across the high-voltage bus.
Which can blow the capacitors.
Oh, absolutely. It physically destroys the inverter.
So a microsecond-level noise issue creates a 50 millisecond data drop, which physically destroys the inverter.
Yeah.
That is just brutally fast. And speaking of physical destruction, we have to look at the sensor connections. The analysis highlights fretting corrosion on the low-voltage pins due to engine vibration.
Yeah, this one is sneaky. You have to keep in mind that an internal combustion engine is basically a massive vibration generator.
Right.
It typically produces these random mechanical frequencies between like 100 and 1,000 hertz, and those vibrations travel straight through the chassis and directly into the sensitive low-voltage connectors.
Including the resolver sensors, right? The ones that track the motor's exact rotational position.
Exactly.
The teardown analysis notes these vibrations cause the connector pins to slide back and forth against each other by just 10 to 100 micrometers.
It's microscopic.
Yeah. It's like rubbing two tin cans together 1,000 times a second.
The tin can analogy is close, but it's actually much worse than just physical wear and tear.
Oh, so...
Well, standard automotive connectors are often plated in tin, and under that intense high-frequency microvibration, the soft tin plating actually scrapes off.
Okay.
Which exposes the underlying metal, which immediately oxidizes.
Oh, and tin oxide is an electrical insulator, not a conductor.
Precisely. So the buildup of this oxidized debris acts as a microscopic wall. The electrical resistance of that connection will spike from under 5 milliamps to over 100 milliamps in literally an instant.
Which just blinds the system.
Completely blinds it.
Because the moment that resistance spikes, the resolver sensor loses its phase lock. The control system has absolutely zero idea what position the motor is in, and all torque coordination instantly fails.
Right. And this brings up a pretty terrifying reality of powertrain engineering.
Yeah.
I mean, we just outlined 4 catastrophic failures, right?
Yeah. Divergent resonance shattering gears, magnetic saturation breaking the math, electromagnetic noise scrambling the data bus, and fretting corrosion blinding the sensors.
Right. And all of these occur in milliseconds. So human reaction time is completely, utterly useless.
Right. You couldn't physically move your foot to the brake pedal before the system tore itself apart.
Not a chance.
So if the hardware is failing at literal lightning speeds, how on earth is the software detecting a microscopic pin failing before the gear fractures?
Well, the system utilizes a heavily layered real-time diagnostic architecture. It doesn't wait for a failure to manifest physically.
Okay.
It constantly audits the underlying physics of the car. And the first layer of that is the dynamic power balance calculation.
The real-time energy accountant. Exactly.
I was looking at the parameters for this in the source material. It calculates the mechanical power, which is the torque of the engine and motors multiplied by their rotational speed, right?
Right.
And then it compares that against the electrical power, which is the high voltage battery voltage multiplied by the current.
And according to the first law of thermodynamics, once you account for map thermal and mechanical losses, those two equations must perfectly balance every 100 microseconds.
Every 100 microseconds, it's checking this.
Yes.
But the trigger threshold caught my eye. The diagnostic flags a critical P0A7F error if there's a 15% error between the mechanical and electrical power, or a 50 Newton-meter torque gap, but it has to persist for exactly 15 milliseconds.
Yeah.
15 milliseconds. Why not flag it after 1 microsecond if it's this closed-loop system?
Because if the threshold is too tight, the system will trigger false positives every time you hit a pothole or experience a minor voltage ripple.
Oh, that makes sense. Yeah, so that 15 milliseconds is strictly calculated based on the vehicle's fault-tolerant time interval, or FTTI.
FTTI, okay.
It is the maximum amount of time the powertrain can operate in a faulty state before vehicle dynamics become hazardous to the driver.
So it's the absolute bleeding edge of the safety margin. It catches a phantom energy leak in 15 thousandths of a second.
Exactly.
But what about the sensor data itself? Like, if the system is relying on sensors that might be corroded, as we just talked about, how does it know it's not being lied to?
Through a highly aggressive speed plausibility cross-examination.
I love that phrase, cross-examination.
It's exactly what it is. The architecture never trusts a single source of truth for the rotor speed. It triangulates.
Okay.
So it takes data from the physical resolver sensor, which is the RDC. Then it compares that against a sliding mode observer, or SMO.
And the SMO, that's a purely mathematical estimation, right?
Yes.
It calculates speed by looking at the electrical back electromotive force, the back EMF that the spinning motor generates.
Right, it's looking at the voltage coming back. And finally, as a third check, it pulls the physical wheel speed data from the chassis ABS sensors.
Okay, so you have a physical motor sensor, a mathematical electrical model, and the physical chassis wheel speed.
Exactly.
The logic matrix for this in the documents is just brilliant. Like, if the chassis sensors say the wheels are doing 40 kilometers an hour, and the SMO math model is seeing high back EMF voltage being generated, but the physical resolver sensor is reporting 0 RPM, the system immediately deduces that the resolver is compromised.
Right. It knows a wire just snapped, likely due to that fretting corrosion.
And the matrix works in reverse too, right?
Oh, yeah. If the resolver, the math model, and the wheel speeds all drop to 0, but the inverter is pushing massive electrical current into the motor.
It instantaneously diagnoses a mechanical lockup.
Exactly. The motor is physically jammed, and the system knows it needs to kill the torque right away before it snaps an axle.
Man. But to run all this cross-examination and the power balance math and the active damping without a single microsecond of latency, that requires massive computational overhead.
Huge overhead, yeah.
The documentation specifies this thing called a Dewar-Checker heterogeneous dual-core architecture.
Yeah, it's a fundamental requirement for ASIL D safety compliance, which is the absolute highest automotive safety standard.
Okay.
Because if you run all this math on just one processor, and that processor experiences a single bit flip, maybe from a cosmic ray, or just a tiny voltage dip.
Hey, a cosmic ray, like radiation from space?
Yeah, it happens. And if it flips the wrong bit, the car could wildly accelerate.
That's terrifying. So the classic analogy for this dual-core setup is having a pilot flying the plane and a co-pilot watching their every move.
Right.
But reading through the memory architecture notes, it feels less like a co-pilot and more like a real-time cryptographic auditor.
I think that's a much more accurate way to look at it, actually. The main core, the doer, is actively calculating the FOC algorithms and driving those fast CC switches.
It's flying the plane.
Right. But sitting on the exact same silicon die is the checker core. And it's not flying the plane at all. It calculates a strict, completely independent safety envelope based purely on the raw sensor inputs.
Okay. And if the checker core mathematically proves that the doer core's next command will push the hardware outside that safe envelope.
It bypasses the software entirely.
Wow.
It triggers a hardware cutoff, physically severing the PWM drive signals to the inverter in under 100 microseconds.
So it guarantees that a runaway software glitch can never manifest as unintended physical acceleration.
Exactly. It just cuts the cord.
So let us assume the worst case scenario then. The power balance fails, the cross-examination catches a severed wire, and that cryptographic auditor hits the kill switch. The documents state the system must reach a safe state within a 60 millisecond FTTI. But what does a safe state actually look like? Like, if you kill the power on a motor that's spinning at highway speeds, doesn't that create a whole new set of physics problems?
Oh, it creates a massive problem. And this is where the fallback safety net kicks in. And it is highly speed dependent.
Okay, let's break that down.
So let's look at the high-speed save scenario. If the drive motor is spinning at, say, 7,200 RPM when a critical fault occurs, you cannot simply open the contactors and turn off the electronics.
Wait, why not? I mean, if the system is failing, shouldn't just pulling the plug be the safest option?
Well, because a permanent magnet motor, if it's spinning at 7,200 RPM, it's essentially an incredibly powerful generator.
Right.
So if you just open the circuits, all that kinetic energy in the rotor has nowhere to dissipate.
Oh.
You'll instantly convert into this massive back EMF voltage spike.
Oh, I see.
And that spike will avalanche back into the inverter, vastly exceeding the voltage limits of the silicon, and literally physically detonate the power modules.
Wow. So you can't open the circuit without blowing up the hardware.
No.
How does it safely scrub that much energy in under 60 milliseconds?
It utilizes a highly counterintuitive maneuver. It's called a stepwise active short circuit.
Short circuit.
Yeah. The controller intentionally short circuits the motor phases together.
Hold on. If you short circuit a generator spinning that fast, shouldn't that instantly melt the copper stator windings from the thermal load? Like, how does it survive its own short circuit?
It survives through incredibly precise timing. If they shorted all three phases instantly, the mechanical shock and the thermal spike might indeed destroy the motor.
Right, it would just lock up.
So they do it in 2 microsteps. First, the controller shorts only 2 of the motor phases together, and it does this for exactly 1.5 milliseconds.
Just a fraction of a second.
Yeah, and this creates a controlled, asymmetrical magnetic drag. It absorbs the initial shock and dampens that first voltage spike.
And then, after that 1.5 millisecond cushion, it shorts all 3 phases together.
Yes. By shorting all 3 phases, the generated electrical energy is trapped. It just circulates harmlessly within the motor's heavy copper windings, where it's dissipated as heat to the cooling jacket.
Wow.
And this artificially clamps the high-voltage bus strictly under 720 volts. So it completely saves the inverter from an explosive overvoltage event.
That is just... It's counterintuitive that violently destroying the circuit temporarily is the only way to save the vehicle's architecture.
Yeah, it's wild.
Does it do this at low speeds too?
No, because at low speeds, a 3-phase short circuit acts as an incredibly aggressive electromagnetic brake.
Oh, right.
If you triggered that at like 20 kilometers an hour, it could violently lock the wheels and cause a severe skid.
So it uses a different protocol, a low-speed save protocol.
Exactly. Below roughly 2,000 RPM, the back EMF voltage just isn't high enough to threaten the inverter anyway.
Okay.
So the system executes an active open circuit, or AOC. It simply drops the PWM signals and lets the motor freewheel, which allows the driver to just coast safely to the side of the road.
It is remarkable that the controller has to dynamically calculate the physics of its own failure mode and then choose between an active short or an open circuit, all in microseconds.
Yeah, the logic is incredibly robust.
But, you know, catching a failure is still a failure. The ultimate goal of the engineering team is to prevent the root cause entirely, right?
Of course.
So let's shift into the DFMEA, the design failure mode and effects analysis. How do they actually design these specific vulnerabilities out of the architecture?
Okay, well, let's go back to our first major vulnerability, that torsional resonance.
Right, the destructive swing effect that shatters the planetary gears.
Exactly. To solve this, they don't just beef up the mechanical gears with heavier steel.
Which would just add weight and reduce efficiency anyway.
Right. Instead, they solve a mechanical problem with advanced software logic. They use a Kalman shaft observer.
A Kalman filter, you usually see that in, like, aerospace navigation and rocketry for trajectory estimation, right?
Yeah.
How are they applying that to a transmission axle?
Well, the engineers embed a highly precise mathematical twin of the physical drivetrain directly into the control chip.
A digital twin.
Yes. This virtual model factors in the mass of the gears, the stiffness of the steel shafts, the damping coefficients, everything. And it calculates, in real time, exactly how the physical metal is going to twist and deform under those engine torque pulses.
So the controller knows the axle is about to ring like a turning fork before the physical metal even begins to flex.
Exactly. And because it predicts the torsion with basically zero mechanical delay, it calculates and injects an anti-phase damping torque from the electric motor at the precise microsecond needed.
That is amazing.
It effectively acts as predictive noise cancellation for solid steel. It attenuates the resonance vibration by over 20 decibels.
That is so cool. Predictive noise cancellation for solid metal. Okay, so that neutralizes the mechanical resonance. But what about the digital side? We talked about that doer-checker dual-core setup. But the documentation details a specific vulnerability where the two cores might try to read and write data at the exact same time, which would scramble the torque commands.
Oh yeah, that's a classic software race condition.
Right.
So when the doer and checker cores share critical data arrays, like, say, the target torque or the rotor angle, there is a high probability that the doer core might attempt to read a memory address at the exact microsecond. The checker core is halfway through updating it.
So the doer core grabs a hybridized, corrupted string of data, half old command, half new command.
Right, and you can't have that.
So how do you prevent that when the cores are operating asynchronously? The DFMEA lists something called lock-free double buffering using hardware semaphores. How does a hardware semaphore actually lock memory?
Well, it operates down at the base microprocessor instruction level. A hardware semaphore is basically a dedicated physical register right on the silicon. Okay, before the checker core writes new data, it sets a physical flag in this register. And if the doer core tries to read that memory block, the hardware physically blocks the read instruction until the flag is cleared.
But doesn't blocking the read instruction introduce latency? Like if the doer core is paused waiting for data, couldn't that trigger that 15 millisecond fault timer we discussed earlier?
And that's where the double buffering part comes in.
Okay, tell me about that.
The system uses two identical memory blocks. The doer core always reads from block A, while the checker core writes the new data over to block B.
Oh.
Yeah. And once the write is complete and mathematically verified, the hardware semaphore instantly swaps the pointers in a single clock cycle.
So it just flips which box they're looking at.
Exactly. The doer core never waits, and it never reads corrupted data. It ensures 100% time and space alignment for all those torque commands.
It's an incredibly elegant solution for what is basically a digital traffic jam.
Very elegant.
And speaking of elegant solutions, let's address that magnetic saturation issue. You know, when the stator gets full of magnetism at high loads or under high thermal stress, and the math model just decouples.
Right, the pullout event. So to manage this, the software relies on dynamic adaptation, because the physical properties of a motor change wildly as the temperature climbs toward like 150 degrees Celsius. So what the engineers do is map out every possible state of magnetic flux and embed it into a 2D LUT.
A two-dimensional lookup table.
Exactly. And it's flashed right onto the controller.
It's essentially a massive multidimensional database of how the motor behaves when it's failing or pushed to its absolute limits.
Yes. And combined with algorithmic techniques like recursive least squares or RLS, the system continuously monitors the stator temperature and the phase currents.
Okay.
And it dynamically recalculates its own fundamental control parameters on the fly. It constantly references that database to compensate for the changing physics of that saturated iron core.
Man, so it literally bends its own math to accommodate the degrading hardware.
It does. And it keeps the torque estimation error strictly under 3%, even when the motor is near its melting point.
That's incredible. And when we talk about hardware degradation, we have to look at the golden fix for the fretting corrosion. We established earlier that engine vibrations cause those tin-plated sensor pins to scrape and oxidize, creating microscopic insulators. Right?
Yes.
The DFMEA solution for this is just beautifully brute force material science.
Oh, it really is. They simply mandate gold-plated terminals for all ASIL-rated safety connectors.
It feels almost too simple, honestly, after discussing Kalman filters and hardware semaphores. But why gold?
Well, because gold is highly noble and incredibly stable. Unlike tin, gold does not oxidize, even when it's subjected to the intense, continuous microvibrations of a hybrid powertrain.
So even if it rubs, it doesn't matter.
Right, the mechanical scraping might still occur, but no insulative oxide layer can ever form.
So by just switching the metallurgy, they permanently lock the electrical contact resistance at a microscopic 1 to 3 milliamps for the entire lifetime of the vehicle.
It completely cuts off the physical chain reaction that leads to that sensor blindness. The design, on paper, is functionally bulletproof.
Right, on paper. But a theoretical design doesn't survive contact with reality if the manufacturing process introduces flaws.
That's the truth.
A perfect schematic doesn't really matter if an assembly worker misses a step or, a machine misaligns a component, which moves us into the PFMEA, the process failure mode and effects analysis. How are they controlling the actual physical build process on the factory floor?
Well, the automotive industry has shifted aggressively toward just removing human variance entirely from critical assembly steps.
Okay.
Let's look at the high-voltage bus bar connections and the structural bolts that hold the motor housing together. Traditionally, an assembly technician might use a pneumatic impact wrench to run those bolts down, right?
Yeah, that's what you always picture in a garage. But the PFMEA strictly bans pneumatic tools for these joints. Why is a standard impact wrench a liability here?
Because pneumatic tools rely on air pressure and mechanical hammering, and that offers terrible precision. If a bolt on a high-voltage bus bar is torqued even slightly below spec, the clamping force is inadequate.
Right, it's too loose.
And those microscopic gaps increase the contact resistance of the joint. Now, when you try to push 300 amps of current through a high-resistance joint, it generates extreme localized heating.
Which degrades the surrounding insulation.
Exactly. And eventually that cascades into a full thermal runaway and a vehicle fire.
Yikes. So what is the mandatory tooling if they can't use pneumatic wrenches?
They mandate closed-loop DC servo newt runners.
Servo newt runners.
Yeah. These are highly advanced network precision instruments. As the driver tightens the bolt, it monitors the exact torque applied and the physical angle of rotation in real time. It maps a continuous torque angle curve.
So it's mathematically verifying the mechanical stretch of the bolt itself as it turns.
Yes. It guarantees that the final clamping force is exactly what the engineers modeled back in the DFMEA phase. It keeps the deviations strictly within plus or minus 3%.
That's incredibly tight.
It is. And if the curve deviates, say if a tiny piece of dirt gets caught in the threads, the tool immediately red lights and halts the entire assembly line.
Wow, so zero guesswork.
Zero.
And there are fascinating digital control at the very end of the line, too, right before the vehicle is cleared for shipping. It's called the end of line, or EOL cloud lockout.
This is a really cool system. So once the physical assembly is entirely complete, the powertrain must calibrate itself. It executes this automated zero-position learning routine, sometimes called ROL.
Okay, what does that do?
The vehicle automatically spins its own drive motor.
Yeah.
And it utilizes this complex signal injection to map the exact microscopic magnetic zero point of its specific physical rotor.
Okay.
And then it writes that unique offset data straight to its internal flash memory.
So the software basically marries itself to the specific physical quirks and variances of the exact motor it was bolted to.
Exactly.
But what if that calibration is slightly out of spec, or the software version isn't perfectly up to date?
Well, this is where the cloud architecture takes over. The vehicle calculates a cryptographic checksum of its flashed software, an SHA-256 hash, and it transmits it to the factory's manufacturing execution system, the MES.
The central brain of the factory.
Right. The MES compares that hash and the calibration data against the master cloud database.
And if there is a single bit out of place, like it just doesn't match.
The MES physically locks the product in the system. It will literally refuse to generate a shipping manifest or print the VIN label.
Whoa.
Yeah. The vehicle cannot physically leave the factory floor until a senior engineer connects to it and resolves the discrepancy. It is a hard, unbypassable digital gate.
It essentially holds the physical car hostage if the digital math doesn't check out.
Pretty much.
That's intense. And while we're on the topic of uncompromising inspections, the PFMEA also details 3D X-ray inspection for the critical logic boards.
Oh yeah, automated X-ray inspection, or AXI.
AXI, right.
100% of the critical safety microprocessors and power management ICs are subjected to a CT scan level inspection immediately after they come out of the reflow soldering oven.
So they are scanning beneath the physical chips to look at the microscopic solder balls connecting the silicon to the fiberglass PCB. What exactly are they looking for that a visual inspection or a camera can't catch?
They are specifically looking for microvoids.
Microvoids.
Yeah, tiny air bubbles trapped inside the molten solder during the cooling process.
Okay.
Because remember, we spent a lot of time discussing the severe 100 to 1,000 hertz vibrations from the combustion engine.
The tin can vibrations, yeah.
Right. If there's a void, an air bubble, inside a solder joint, it creates a structural stress concentration point.
So over thousands of miles of engine vibration, that tiny air bubble will initiate a microscopic fatigue crack.
Exactly. A crack that will propagate until it completely severs the physical connection between the processor and the board.
Which would cause an instantaneous catastrophic loss of vehicle control.
Yeah, going 70 miles an hour down the highway.
The tolerances specified here for this test are incredibly strict. I read that the AXI algorithm will scrap the entire control board if there is more than 5% total voiding across all the joints combined, or if any single air bubble is larger than 1% of the joint's volume.
Yeah, they do not mess around. It guarantees the physical foundation of the digital brain can actually survive the life of the car.
Okay, so we have mathematically verified bolt stretching, we have hard cloud lockouts, and X-ray vision for the silicon. The design and the manufacturing process are locked down.
They are.
But trusting the process is not enough. Before a single unit is authorized for mass production and put into a customer's driveway, the engineering teams have to empirically prove the limits of the hardware. They have to torture it.
Oh, they absolutely torture it.
Which brings us to the DVP&R, the Design Verification Plan and Report.
The validation phase is really where we see just how aggressively engineers will attack their own architecture. Let's look at the mechanical and thermal endurance testing, which is often referred to internally as the shake and bake.
The shake and bake. The parameters for this test in the notes are just staggering. They mount the powertrain control units onto these multi-axis shaker tables and subject them to random, violent 3D vibration and 35 meters per second squared of acceleration.
Yeah, it's intense.
Sweeping continuously across a frequency band of 10 to 2,000 hertz.
It is an engineered simulation of the absolute worst possible physical roads and engine misfire harmonics combined together.
Right.
And while it is violently vibrating like that, they seal it in an environmental chamber and subject it to aggressive thermal shock cycling.
Plunging the ambient temperature down to negative 40 degrees Celsius, so deep freeze, and then spiking it rapidly to positive 125 degrees Celsius, which is significantly hotter than boiling water.
And the critical factor here is that the controller isn't just sitting there off,
Yeah.
It is actively powered on and running at maximum computational load, driving simulated maximum torque for over 1,000 continuous hours.
Over 40 days of non-stop violent shaking and boiling to freezing temperature swings. And the pass-fail criterion is what makes this so insane. Over those 1,000 hours, across millions of data frames, there cannot be a single electrical signal drop lasting longer than 1 microsecond.
A single microsecond dropout constitutes a complete validation failure. Start over.
Man! And even if it maintains perfect signal integrity, the engineers don't just take the data's word for it, do they? They pull the units off the shaker table and perform a destructive physical analysis.
Yeah, they do.
They literally cut the circuit boards and connectors into cross-sections.
Yes. They pot them in epoxy, slice them open, and inspect them under scanning electron microscopes.
To prove what?
To prove empirically that the gold plating didn't fret and that the X-ray verified solder joints did not develop microscopic stress fractures from the shake and bake.
That is just so thorough. So that proves the mechanical resilience. But what about the digital resilience? We highlighted those screaming silicon carbide chips blasting out electromagnetic interference and scrambling the CAN network. How do you validate that the software architectures, like the hardware semaphores we discussed, actually filter out that noise?
They validate it in what they call the electromagnetic war zone through bulk current injection or BCI testing.
Okay, what is that?
They place the entire controller ecosystem inside an anechoic isolation chamber, and they simulate a nightmare scenario of EMI noise.
The documentation shows they bombard the components with high-frequency dynamic radiation fields peaking at 100 volts per meter.
Yeah, they're basically saturating the air with invisible electromagnetic energy. And simultaneously, they're using coupling clamps to inject 200 milliamps of raw, chaotic current directly into the data and sensor wires across a massive frequency sweep.
They are forcefully injecting the exact common mode interference that those CX chips generate, actively trying to scramble the communications.
Exactly. And through all this digital warfare, the controller has to maintain a signal-to-noise ratio of at least 48 decibels.
So it proves that the digital filtering and the differential signaling on the circuit board are so robust that no matter how much electrical static is bouncing around the engine bay, the controller will never misinterpret a noise spike as a valid torque command.
It will never hallucinate a command, yeah.
Which brings us to the final validation gateway, and honestly, it is easily the most fascinating part of all this. The hardware-in-the-loop fault injection, or HI.
HIL testing. This is the matrix.
The matrix.
It really is. HIL testing is where the physical world and the digital world collide to test the ultimate safety nets.
They take the actual physical powertrain controller, the finished brain of the car, and plug its sensor inputs and motor outputs directly into a massive FPGA supercomputer.
Right. And the supercomputer runs a high-fidelity, real-time physics model of the entire vehicle, the battery, the motors, the road surface, everything, with near zero latency.
So the physical controller fundamentally believes it is driving a real car down a real highway.
They have no idea it's plugged into a computer.
Wow. And the supercomputer spins the virtual motors up to extreme velocities, pushing the simulation to 12,000 RPM.
And this is where the engineers get to play God. While the system is at maximum load, they intentionally inject catastrophic software bugs and hardware faults directly into the simulation.
They are actively trying to induce those pull-out stalls and the over-voltage surges we discussed at the very beginning.
Yep. They might program the supercomputer to instantly drop the CAN communication network for exactly 50 milliseconds, simulating a total data blackout.
Or they will inject a sudden, violent 45-degree error into the simulated rotor position data, which instantly shatters the controller's FOC math model.
They are triggering the worst-case scenarios at the absolute worst possible time.
So what is the success metric here? What must the physical controller do to pass this nightmare test?
This is where everything we discussed today has to perfectly synthesize. The safety checker core, our cryptographic auditor, it must independently detect the injected hallucination or data drop in under 60 milliseconds.
The FTTI.
Exactly. It must override the doer core and immediately trigger the stepwise active short-circuit protocol.
It has to execute that 1.5 millisecond two-phase short, followed by the three-phase short, to trap the generated energy.
Yes. And the documentation adds two final brutal constraints to this. When it triggers that short circuit at 12,000 RPM, it must manage the current so perfectly that it stays strictly under 550 amps.
Under 550 amps. Why that specific number?
Because if the short circuit current spikes above 550 amps, the immense opposing magnetic field will permanently demagnetize the rare earth magnets inside the motor rotor.
Oh, which would physically destroy it.
Yeah.
And mechanically, the torque ripple, the violent physical shudder sent through the drivetrain as the motor slams into a short circuit, that has to be attenuated by the software to under 5 Newton meters.
Exactly. Which basically means that while the controller is fighting a literal life or death battle to prevent a 720-volt explosion in a fraction of a second, the driver in the cabin feels nothing more than a faint vibration in the steering wheel.
That is insane.
And only when the architecture proves it can execute that flawlessly, thousands of times in the simulation, is the software signed off for human use.
I mean, let's just take a breath and zoom out for a second. The journey of engineering here is staggering. We started with the chaotic reality of an internal combustion engine vibrating and basically trying to tear gears apart.
Right.
And to control it, engineers had to build a digital architecture that calculates thermodynamic power balances in 100 microseconds. They built a dual-core silicon auditor that can sever hardware connections in milliseconds. They engineered virtual axle models to cancel resonance, mandated brute force gold plating to beat microscopic oxidation, and utilized CT scanners to find tiny air bubbles.
That's exhaustive.
And finally, they tortured the physical hardware with radiation and extreme thermal shock while a supercomputer injected nightmare software bugs. And all of this immense invisible effort exists solely so that when you press the accelerator to merge onto the highway, the vehicle simply goes seamlessly.
It really redefines what we consider a vehicle to be. The physical hardware is almost secondary to the computational control governing it.
It really is, and I want to leave everyone with a final thought on that exact point. At the very end of the source documentation, there is a technical addendum detailing the capability to build highly precise Python simulations of this entire powertrain.
Oh, the digital twins.
Yes, the kind meticulously models the engine's combustion pulse waveforms, the specific damping coefficients of the dual-mass flywheel, and the microscopic startup torque ripples of the electric motor.
It's a flawless, fully realized digital twin of the mechanical hardware.
Exactly. We are rapidly moving into an era of engineering where we don't really build cars anymore. We build perfect digital twins of them first. Every single vibration frequency, every potential phase lag, and every microsecond processing delay is mapped, tested, and entirely resolved in a virtual mathematics environment before a single piece of real-world steel is ever cut or cast.
It's a completely new paradigm.
It is. So when a vehicle race fundamental safety relies entirely on closed-loop map executed every 100 microseconds, it begs a fascinating question. Is the physical car sitting in your driveway actually the core product of this engineering? Or is the physical car just a real-world metallic printout of an idealized mathematical equation? Something to mull over the next time you put your hybrid in drive and merge onto the highway. We'll see you next time on The Deep Dive.